Thank you so much. Thank you everyone for coming. Whatever time zone this works out to be for you, this worked out to be not too bad for me. Um, so I'm going to talk about serpentine and oceanic transform faults today. Um, but I'm also, when I was putting this talk together, I could very easily have done um, uh, slides that look like this as the title slide. And that's because we actually got into port 1 week ago today from sampling the chain transform fault in the equatorial Atlantic. Is a very successful cruise. We had a great scientific party on board. A couple of them are on this call right now. And I'm going to talk about some of the results from that at the end of this talk, which is obviously very much, we're still processing through everything that we found, but I'm excited to show some preliminary images from that. Um, so oceanic transform faults, for me, one of the big motivations to study them is to try to understand this observation about them globally, and that is that they only have about 20% of their expected seismicity. We know what the plate slip rate is, or the fault slip rate is, and you can model what the area is and then predict how much seismicity they should have. And on average, that works out to be an 80% seismic deficit. Fault to fault, it varies a little bit, but when you think about transform faults in comparison to looking at continental transform faults, this is a really nice figure from Bone and Steele's paper in 2005, showing that on land, earthquakes, right, account for most of the slip on strike slip faults. But once you're in the oceans, earthquakes account for a very small proportion of that. And then a lot of the movement on these faults is aseismic slip. And I'm interested in rheology and how rocks deform. And so that leads me to this question of what is it that's going on in the rocks on these oceanic faults to cause that. Just to think about that seismicity in a little bit more detail, this is the chain transform fault, which we just got back from last week. So this is on the Mid-Atlantic Ridge, and I'll show a location map later on, but this is the Mid-Atlantic Ridge here, Mid-Atlantic Ridge here. The triangles are just the dredging that had been done prior to our cruise. And then this is this beautiful 300-kilometer long transform fault. This is a figure that Margaret Betcher put together to show how the seismic coupling varies along the fault. So you have sections of it that have almost no large earthquakes, and then you have sections like this one here that seems to be almost fully seismically coupled. Then these regions that we call aseismic, though I should say that they do have lots of small earthquakes, but they lack the large ones that can be seen teleseismically. And then you go back into another seismic section of the fault. And this is kind of classic behavior that we see along all of the oceanic transform faults, that sections of it have the large earthquakes and other sections don't. This figure I put together is actually from when we wrote the proposal to emphasize the fact that if we want to understand what's going on in these faults, then we need to get some samples from the fault itself. And the only sampling that had been done in the case of this one is dredging that had been done in the late 60s. And so this was one of the reasons that we were very interested in chain. Another reason that we wanted to sample these faults is that if you ask kind of people that just in general, what their impression is about why there is not a lot of seismicity on the faults, the standard explanation that you'll get is that there is serpentine present in these faults. And so this goes back, I think from what I can tell in the literature, to work that Enrico Bonatti did. This is from his 1976 paper, as well as subsequent work that he did with McDonald. This is from the 1986 paper. And one of the arguments, this is a cross-section of the Vima transform fault, another one of our equatorial Atlantic faults. And they said, okay, here's the transform fault zone. And the argument was that this is mainly composed of basalt and gabbro crust with serpentine screens. But if you look at what had been recovered from that, the serpentinite that had been recovered was actually coming from the valley wall, and there's no direct observation that we could find of serpentine actually in these fault zones themselves. And so this actually led me to start looking to see if there were samples of serpentine myelinite from any of these faults. And therefore, if we could actually take serpentine myelinite and use them to understand or to place better constraints on what's going on in this strike slip setting. And so this is now just a map showing globally everywhere where the transform fault itself has been sampled. Sorry, there's a fly buzzing around here. So this is the Shaka transform fault. This is now in the South Atlantic on the Southwest Indian Ridge. So this was work that we were doing looking at existing samples Shaka is one of the locations I like a lot because the dredging there happened to recover a lot of samples. A couple of these places that are labeled as having fault zone samples have very few samples available to study. Shaka is really nice because there was about 7 dredges done, of which 3 recovered a lot of fault zone samples, and a lot of mylanites were recovered from there. This is now a figure from Cécile Prigent's work when she was a postdoc in my lab, just showing this is the Shaka transform fault here. The blue circles are just the teleseismic earthquakes that have been recorded on this fault. And then the red stars are showing where the dredging was done. This was dredging that was done in 1980. These are some of the largest dredges of deformed samples that I know of in the US seafloor sample collections. And she put together a composite profile from that bathymetry of, roughly speaking, where dredge 60 and then 61 were in this transect. So as best we can tell, and this is not that much bathymetry and not a lot of constraints, but it seems like the fault zone in this case is associated with this small bump on the seafloor. And when we've gone through the hundreds of samples in these dredges, they are a mixture of a small amount of breccias and then predominantly prototype myelinite, and then a small number of serpentine mylanites. We went through those samples in detail, and it works out that you have about 16% serpentine or serpentinite myelinite. So that seemed like, okay, we're starting to get samples that are the serpentine from these fault zones that could explain the lack of seismicity. But it's also not a lot of the samples that are coming there. And there are, possible reasons for this. This could be just bias due to dredging, right? Dredging is, it's a very efficient technique for sampling the seafloor, but it's not able to give us, super in-depth detail of what we're actually sampling. That's particularly a concern if we're looking at a very narrow fault zone that, we know from on land that those fault zones tend to be, the core of the fault zone should be less than 100 meters wide, right? So we're sampling up, Shaka is something like 5 kilometers below sea level is where we're sampling, right? So we're sampling from the ship. We're trying to sample at 5 kilometers depth. We're looking for a zone that is 100 meters wide. We know that that is a challenge with doing all of this by dredging. And then, of course, the final reason that there could be very little serpentinite recovered is just that there really isn't a lot of serpentinite. And that's kind of the central question to us, is whether serpentinite is present in the fault zone and is really the explanation for the lack of seismicity in these settings. In this case, we said, okay, we have a whole bunch of samples that can be classified as serpentinites. And these are the set of 8 samples that came out of these dredges that we would call serpentinites. But that's where there's then a big asterisk that comes in because a lot of these samples look like it is just a static replacement of this original prototype myelinite by serpentine. So for example, this sample here, which does have a large amount of serpentine, it's still got a core of original prototype. A lot of these other ones look like they are prototype that is just heavily altered. And so to really test that, we zoomed in on this one sample. It has this fresh core here, or I shouldn't call it fresh. It has a core here of prototype that is then surrounded by a more serpentinized zone here, along with stuff that may or may not be things like talc. And we started looking at that sample in detail. So zooming in on it, this is now a picture from a thin section. And we ID'd the different types of serpentine in there, the cross-cutting veins that seem to be chrysotile dominated based on looking at Raman spectra. So that's all very interesting. But the question still remains, even though we have serpentine now, it was that serpentine deformed. And that was where we started doing EBSD mapping. So looking with electron backscatter diffraction to map out the different minerals in there. This is a map of this little area. The kind of cyan color stuff is olivine, and then these darker bands that were challenging to actually map the minerals in there are a mixture of serpentine and tremolite. But this is where we really started to move away from thinking that even this sample that has a heavy amount of serpentine is actually recording deformation of serpentine. And that's because when you look at the textures in here, you're not seeing aligned foliated serpentine that looks like it underwent deformation. Instead, you have a lot of grains going at odd angles to the general foliation, and that is an indication that the serpentine and the tremolite grew later as a static overgrowth and then not recording deformation. So then kind of after spending a lot of time trying to really get into these samples and thinking of them as serpentine myelinites, to me, these samples are really just prototype myelinites that had seen extensive alteration. But that gets us back to this question about, are we just not adequately sampling these fault zones? And are we missing things when we're doing all of this by dredging? And this is where going back and looking at on land outcrops is useful. This is an example from Diane Moore's work from a 2018 paper of hers showing the Bartlett Springs Fault in California. There's a beautiful outcrop here. And this core of the fault zone is a serpentinite bearing melange. Right. So maybe this is the material that we should be looking for when we're thinking about these fault zones. Maybe we're thinking something more that is like a block and matrix setup. And maybe when we're using dredging, which, is a chain metal basket, right? It's designed for the water to pass through it. Maybe we have this bias due to dredging because we're not adequately sampling everything in the fault. Another thing when you look at this is that this zone in their field observations is 1.5 meters wide. Right. So again, our challenge from the ship, kilometers above the area that we're sampling, is that we potentially just going to have a very challenging setup to really sample this fault zone. And then, of course, there's this question of whether serpentine really is the answer for understanding these fault zones. So all of that gets us. This is just to say this is that most samples, right, that we're looking at for the seafloor being recovered by dredging. And this is what I mean, that this basket, right, you need to have the water be able to pass through it as you're bringing the rocks up. But of course, you don't know what weaker materials or softer, gouge materials or matrix materials might be washed out of the dredge basket as it comes up. So all of this led us to put together this project to do a better job at sampling the fault zone. And this is a National Science Foundation funded project to look at the chain transform fault. We just completed what turned out to be the third cruise for this project. So we sailed out of Cape Verde, which is some islands off of West Africa. It's about a 4-day transit to get down here to chain transform fault. This is that same map that I showed earlier. We had a year ago on the Langsat that deployed seismometers as well as did an active source seismic experiment. So we have a lot of data that's going to be coming online from that. And then the most recent cruise, we were out there with the dredge basket as well as Sentry. And Sentry is an autonomous underwater vehicle that can do geophysical surveys of the seafloor very near bottom, less than 100 meters off the seafloor, and give us very detailed imagery of that. And then dredging in this case, because there is essentially no samples of the fault zone, we decided to target initially with dredging to figure out where it is that to isolate the fault zone itself. But we also did a lot of focus sampling. You can see, hopefully on your screens, we knew from the bathymetry that the fault zone, and when you zoom further in on this map, is this narrow line here. And we know from advances in dredging technique that we can do a better job of actually sampling this fault zone. And so we did that. This is a cruise that we just completed. It was a month long. We sailed into the transform fault here. This is a map that Evan Saltman put together. The red line is everywhere that the ship went. All of these little tiny symbols are dredges that we did. And then in addition, we also had these dives that were done with Sentry. And so we actually spent a lot of time here, moved over to here, went all the way to the ridge transform intersection, came back, did more work here, and then went over and sampled over here in the east. The Sentry dives gives us some really beautiful maps of the fault zone. This is a multi-beam bathymetry map at roughly 1 meter resolution. This is data that has not been corrected for navigation and artifacts. This is just the kind of raw first pass look at the data that Sentry was able to collect. It did a map. This was focusing in on that narrow ridge that I was showing on actually, let me go back one slide. So that map is somewhere in here in this area where we can see that we have that ridge that we think is the fault zone. And that is what it looks like, especially when you start zooming in on the bathymetry, that you have this really narrow fault zone here. That is where the active fault zone is. Using that map, we were then able to go in and do these very short dredging tracks. In the case of these fault zones, we were doing things that were about 500 meters long. But also one of the, there were two, I would say there are two changes in how we were doing the dredging. One is that we were using a mesh bag on the dredge itself that was much finer than what's normally used, and that is able to hold in more material while, of course, letting the water out. And then the other thing was that we were also using ultra short baseline beacon on the dredge to know much better where the dredge basket itself was. And the result of that is that we got a lot of rocks back. So what about the rocks? We ended up recovering over 5,000 kilograms of rocks. So that's about 12,000 pounds of rocks. Out of those, we described about 1,600 samples individually, but everything else got bagged up, weighed, and is now in a shipping container that is heading back to Woods Hole to the Seafloor Sample Repository there. Um, and we did 65 dredges in total. This is actually, we put in to do 30 to 40 dredges. We were incredibly successful with the dredging. This is a really beautiful map that Alex, Janine, Tomas Guillaume and Evan Saltman put together, taking all of the statistics from the dredges in terms of lithology as well as what is deformed. So these are the 65 dredges. We all learned some French on the cruise thanks to our French participants, which is that camembert is the French word for pie chart. So these are the camemberts that they put together from the dredge statistics. You can see from the red, we have a bunch of brittly deformed stuff. From the orange, there's also ductilely deformed stuff. This is a lot of rock to go through. There's a lot of thinking that we need to do, and that is why I'm going to get to take home messages and leave you without a clear punchline in terms of the serpentine. Pre-cruise, what I would have said is that the existing samples we have of serpentinite myelinite do not show evidence of serpentine deformation. And so that would suggest from what we knew previously that serpentine was not a good candidate to describe the lack of seismicity. Post-cruise, we now have 65 dredges that we're working through analyzing. We have a whole bunch of breccias of myelinite. We have some stuff that looks serpentine hosted, but we are in the very early stages of figuring out what the composition is of some things. There was some stuff that at sea we struggled to really ID what it was beyond saying, well, it's got to be mafic or ultramafic because we're in the ocean. But there's a lot that we're still figuring out. We do know that we have much better sampling of the fault zone because of adjustments to how we were doing the dredges, as well as really targeting that very fine area in the middle of the Transform Valley with the dredging. So I think I'm a couple minutes over, and I will leave it at that, and I'm happy to take questions.